We now turn to the subject of evolution of galaxy clustering. But before we get into that subject proper, we have to introduce another concept. This is the concept of galaxy biasing, which we did mention before. And the way it works is like this. In principle, visible material, galaxies, stars in them, may not be distributed in exactly the same way as the dark matter. It turns out that by and large they are, but at some scales that need not be the case. And so we simply introduce the possibility that density contrast in baryons is some factor b times the density contrast in the dark matter. And when expressed through the two-point correlation function, then the correlation function of visible material is factor of b squared times the correlation function of the dark matter. Note that there is no assumption that one is stronger than the other. If b is greater than 1, then baryons, or visible light, are clustered more strongly than dark matter. And if it's less than 1, then the other way. And so it is possible that the visible material is not entirely representative of the underlying mass distribution, but it gives you a biased answer, and thus the name of galaxy bias. Now, why could that be? And so one possibility is that as the structure forms, it forms in the density peaks of the primordial density field, and it may start forming faster or go further in the densest spots. So those would be the high peaks of the density field instead of average or 1 sigma deviations or 2 sigma deviations. Those could be 5 sigma deviations. And that turns out that for just about any type of noise, it is true that the highest density peaks are clustered more strongly. So here is an example of this. Let's take a just exaggerated density cut through a density field in the early universe. And you can think of it as small-scale fluctuations riding atop of large-scale fluctuations, or large-scale fluctuations lifting the small ones even further. So if you impose a threshold, saying it has to be at least this dense for galaxies to really form, to ignite star formation and so on, then it's those fluctuations that are lifted by the large waves that will start doing it first. And by the construction of this, they'll be clustered strongly together. And so you'd expect then that the first structure, galaxies, form in the highest spot of the density field, the deepest potential wells, and that you might see formation of protoclusters. On the other hand, there can be protovoids, which are negative fluctuations. Things are less dense than the other places. Let me give you a metaphor for this. Imagine asking that on the planet Earth, what are the highest points above the sea level? And if you were to put that cut at a few kilometers elevation, you'll find out that all of them are concentrated in areas like Rocky Mountains or Himalayas or Cordilleras and so on. And then as you slowly lower down the threshold, more and more land is enclosed, and eventually the entire surface of the planet Earth is enclosed. Same thing here. The highest points will be by nature clustered together because they correspond to smaller fluctuations atop of larger ones. Here is a direct illustration of this, not from real universe, but from simulated one done by Ray Kalberg. So he followed the formation of the structure and then asked, there is some average value of the density and there are deviations of it. And so what is the distribution of all data points? Then just those that are higher than 1 sigma above the mean, 2 sigma, 3 sigma. And you can see that as you increase the threshold, they get to be clustered more and more strongly. They all pile up in just one part of the slice. So now we can estimate this from redshift surveys. Redshift surveys, as you recall, give us actual measurement of the mass distribution because by decoupling Hubble expansion peculiar velocities, we can find out where the mass really is that causes galaxies to move. And we can also see where the galaxies are. So we can directly compare the distribution of mass inferred from redshift surveys with those of galaxies themselves. And so here is a plot from Sloan Redshift Sky Survey, and plots the value of the bias as a function of galaxy luminosity. And you find out that past certain luminosity, clustering grows dramatically. More luminous galaxies are clustered more strongly. And this makes sense in the previously described scenario, because the earliest forming ones will eventually grow to be the largest ones, and they did form at the highest peaks of the density field, and they will be clustered more strongly. As it turns out, this is also the case at all redshifts, and it's even stronger at high redshifts. So now let's look at evolution of clustering itself. Generally speaking, you expect the clustering to grow in time. As the structures collapse, the density contrast increases. Remember, it starts as a few parts in a million at the time of the recombination, and now grows to a factor of 1,000,000 in galaxies themselves, or a few hundred in large-scale structure. So general expectation is that clustering has to get stronger in time, or conversely, it'll be weaker at higher redshifts. A way to quantify this is to follow the two-point correlation function. And a simple model is shown here. It changes the amplitude of the correlation function as some power of the expansion factor, 1 plus z. And it's written in the following form. So different values of this parameter epsilon correspond to different types of clustering evolution, as indicated here. If epsilon is equal to minus 1.2, then the clustering is fixed in comoving coordinates. It doesn't change, it just expands. If epsilon is 0, then clustering is fixed in proper coordinates. The universe expands, but the structures stay just as they are. And pushing further, if epsilon is positive, that means the clustering will grow in time in proper coordinates themselves. And the observations indicate that that's indeed the case, but not any one single value of epsilon describes this process at all different scales. So let's look at some data. What's plotted here is the amplitude of projected angular two-point correlation function as a function of depth of the survey. Now, the deeper you look, fainter galaxies you see. And so on average, fainter galaxies are further away, or at higher redshifts. And you can see that's exactly what you expect. As you go deeper, meaning further, the strength of the clustering diminishes. But because we actually have redshifts for those, we can follow the strength of the clustering as a function of redshift. And here it's plotted as clustering length, R naught, which you may recall is where correlation function has amplitude of 1, and it's about 5 megaparsecs divided by little h near us. And then as you go deeper in redshift, it goes down. Lower clustering length means weaker clustering. And so here, out to redshifts of about unity or slightly beyond, this is exactly what we expected. But then something interesting happens. Going to larger redshifts, past redshift of 1, the clustering strength starts increasing again with redshift, meaning it's been decreasing in time, which is exactly the opposite what you expect. So even in the deepest redshift survey measurements over very small fields going very deep, pencil beam surveys, we see spikes. And as you may recall, by having pencil beam survey go through large-scale structure, spikes would correspond to intersections with filaments or voids and so on. And here you see them occurring at redshifts of 3 or 4 and even beyond. Turns out the strength of clustering back then, when the universe was only a couple giga-years old, is about the same as it is today. So the clustering got weaker and then got stronger again. And it's not just galaxies. You can use quasars, which we can see very far away, and they tell the same story. Beyond redshift of 1, going to higher redshifts, clustering strength increases, exactly the opposite from what you expect from naive picture of structure formation. So how can this possibly be? And the answer is due to the evolution of bias itself. And here is how it works. Consider the fate of fluctuations of different amplitude, here shown with little thin black lines and dashed red lines. The highest fluctuations, say phi sigma ones, will evolve fastest. They will reach higher values sooner. The lower contrast fluctuations will get there eventually, but takes longer time. Now, if the structures form according to the bias contrast, then as you look back, you'll be looking at different type of fluctuations. Near us, you may be looking at 1 or 2 sigma fluctuations, which are clustered however they are. If you could follow them to higher redshifts, you would see their clustering indeed was lower at larger redshifts. But you don't. You see structures that are corresponding to higher contrast as you go to deeper redshifts. Instead of 2 sigma peaks, you may be looking at 5 sigma peaks, because that's where galaxies are back then. And those peaks were clustered more strongly. In other words, at different redshifts, you're looking at a different sample of objects. And this is, again, why this is called biased galaxy clustering. So this is almost certainly what's happening. By looking at high redshifts, we're looking at the highest peaks of the density field, and they're strongly clustered. And then, as you look at lower redshifts, then you see lower contrast peaks, and they're clustered less. And this is why there is an apparent effect of clustering getting weaker in time. It's not. It's just that you are changing the sample to which you're looking at, from say 5 sigma peaks to 3, 2 sigma peaks, and so on. But all of them increase in time. Each of these density contrasts gets stronger in time. It's just that the highest ones get there first. And indeed, this can be probed with large, deep redshift surveys, and here is a result from one of them, from European Southern Observatory Deep Survey. It shows the value of the effective or average bias parameter for galaxies, starting from redshift of unity to about 1.5. And you can see that it was higher in the past. So galaxies near us are almost an unbiased tracer of underlying mass. Near us, when we look at large-scale structure as painted by galaxies, we see exactly how the dark matter is distributed as well. But as we go deeper in the past, higher redshifts, then we see a more biased set of tracers. Galaxies are more clustered than the underlying dark matter back then, because it's those that are highest density contrast that light it up. And so this is what you see. So to summarize the evolution of clustering and bias, a generic expectation is that clustering grows in time, and it does. But the rate at which it does depends on the mass or the density contrast of the initial conditions, the type of the objects that you're following. And it's fastest for the highest contrast ones. We can quantify this through the evolution of a 2-point correlation function, as shown here. And observationally, we can follow clustering to the highest redshifts we can probe today. Now, what we observe is always light, not mass. And so this is why I introduced the concept of biasing, to allow for the possibility that light, visible parts of galaxies, are clustered in a different way from the underlying mass distribution. The simplest way of quantifying this is saying that they're proportional, and factor of proportionality is b, and it's greater than 1 if light is clustered more strongly than mass, and it turns out usually is. Now, b is not really a constant. It is a function of all manner of things, not just time, but also the density contrast itself, and so on. And there is no analytical theory for its change, but it is something that we can reproduce from numerical simulations and then compare to the observations. And it turns out that at low redshifts, galaxies are a pretty unbiased tracer of the underlying mass. Galaxies have formed fully, by and large. Of course, they keep merging and so on. But as you look at higher redshifts, galaxies become an increasingly more biased tracer of the underlying mass distribution. That is, the deeper in the past you go, the more biased sample of the higher density peaks you see. Next, we will talk about clusters of galaxies.